Hello everyone, my name is Adylxon Nixon from class DP2A. My number matrix is 20 DP 24F 1003. This is my partner.
Hello, my name is Rima. I'm from the EP2A and my matrix number is 20 DEP 24F1004.
Okay. So today we will present about semiconductor devices for practical work too.
So this is our objective. The objective is we able to construct the circuit of half wave rectifier using multimeter to measure voltage and current in the circuit and trace the input and output waveform of half wave rectifier circuit using oscilloscope.
Okay, so what we can learn from our discussion is that we were able to construct a circuit of hardware rectifier. Next is we were able to learn how to use an oscilloscope or oscilloscope traces the input and output of waveform of half-wave rectifier circuit. And lastly, we were able to learn about how to measure voltage and current in the circuit using a multimeter.
So this is the main formula that we are using for the lab. V average equal to 2 Vp over pi. The next one is V average equal Vp over pi. The next one is V out equals to Vp minus Vd, or we can call it V diode. I average equal to V average over RL, and the last one is V average equal to V out over pi.
So this is the procedure for making the circuit. Firstly, you have to connect the circuit as shown in the figure 2.3. Second, we have to choose the step-down transformer of 12 volt and 0 volt. Third, using an oscilloscope, determine the input AC waveform and point A to B and output DC waveform at point C to D. So that means you have to use the oscilloscope and to determine the AC waveform of point A to B and the output DC waveform. Okay. Fourth is to draw the input and output waveform and record the peak voltage, which is VP, obtained in table 1. Fifth is to calculate the VRMS, V average, and the current average, and then record it to the table in table 1. Next, you have to use an analog multimeter to measure the RMS voltage at the point A to B and record the reading in table 1. Don't forget to adjust the multimeter to AC volt range. Next, by using a multimeter measurement, using a multimeter, you can measure the average voltage at point C to D and record the reading in table 1. Also, don't forget to adjust the multimeter to DC volt range. And lastly, insert a multimeter in series with the RL, which is the resistor, to measure the current average. Record the reading in table 1 and don't forget to adjust the multimeter to DC ampere range.
As you can see, this is our result for the lab. Waveform at point A to B, volt per division we got 5 volt, Vp we got 38 volt, and VSC we got 12 volt. For the measure value VRMS we get 12 volt. For the calculate, we need to search the Vp first, and Vp equals to Vpp over 2 equals to 38 over 2, and VPP equals to 19 volt. V out, also we need to use the formula Vp minus 0.7, and V out equals to 18.3 volt. And finally, the VRMS equals to V out over square root 2, and it will be VRMS equal to 12.94 volt. For the waveform at point C to D, the volt per division is 5 volt. The Vp equals to 17 and the VDC equals to 4.94 volt. The measure value for V average is 4.94 volt and the I average is 6.28 ampere. But if we calculate the V average equals to V out over pi. V out equals to Vp minus 0.7, and it will be 70.3 volt, and the V average equals to 17.3 volt over pi equals to 5.51 volt. For the I average, V average over RL, and it will be 5.51 over 1 k ohm, and I average equals to 5.51 milliampere. So this is the question. For question 1, it will present by Ellison Moses, and for question 4, it will present by me. So this is the question. For question 1, it will present by Ellison Moses, and for question 4, it will present by me. So this is the question. For question 1, it will present by Ellison Moses, and for
Okay. The first question is to discuss the DC output voltage observed in table 2.1. So the measurable DC output voltage, we got 4.94 voltage. And then our calculated DC output voltage, we got 5.51. To prove this, we have to use the formula, which is V out equals to V pi. But first, we have to find the V out, which is the formula V out equals to Vp minus Vd. And then we substitute the value into the formula, and then we got 5.51, which is the calculated DC output voltage. So the reason for the difference of value in the between the calculated and the measurement value is because of the voltage drop. Also, the load resistance also affect the output of the voltage, which also been caused by a measurement inaccuracy or a circuit loss. So, the key observation that we can get is that our output confirm a successful rectification, because the measurement value and the calculated value differences is really small, so which means it's a success.
For question 4, discuss the operation of half-wave rectifier. A half-wave rectifier converts AC into DC by allowing only one half cycle of the AC signal to pass while blocking the other half. During the positive half cycle of the AC input, the diode becomes forward biased, allowing current flow through the load resistor and generating output voltage that follows the shape of the positive half of the AC waveform. However, during the negative half cycle, the diode is reverse biased, preventing current flow, and the output voltage drops to zero. As a result, the outputs consist of only the positive half cycle of the AC signal, producing a pulsating DC voltage that require further smoothing for practical DC application.
So, in conclusion, in this experiment, We explore the operation of rectifier circuit and their role in converting AC voltage to DC voltage. By analyzing both half-wave and full-wave rectifier, we observe how different circuit configuration affects the DC output voltage. The measure DC voltage value closely match the theoretical prediction with minor variation due to factors such as diode voltage drop, ripple voltage, and the impact of load resistance. This variation highlights the importance of component selection and circuit design in achieving stable DC output. Also, through our observation, we confirm that full-wave rectifier provide a higher and more efficient DC output compared to a half-wave rectifier. Bridge rectifier, in particular, offers a practical advantage by eliminating the needs of center tap transformer while maintaining the efficiency power conversion.
The experiment demonstrates the significance of rectifier in real-world applications, such as power supplies, battery chargers, and other electronic circuits that require a stable DC voltage. Overall, this experiment enhanced our understanding of rectifier circuit, reinforcing key theoretical concepts of and practical measurement techniques. By applying instantaneous formula for DC voltage and current, we gain insight into the behavior of rectifier under different conditions. This knowledge is crucial for designing efficient power supply systems, ensuring reliable DC power for various electronic devices.
Thank
Thank you
you
for
for watching.
watching.
Thank
Thank
you
you
for
for
watching.
watching.
Thank
Thank
you
you
for
for
watching.
watching.
Thank
Thank
you
you
for
for
watching.
watching.